Hello, in this fourth video we'll see how to run the model, review the different input parameters and explore the outputs. To follow along with this tutorial, I'll assume that you have already installed EVPV on your computer and have collected the geospatial files for your case study. Again, this tutorial mainly follows the steps that are available on Read the Docs, this time here in the section called Usage. Note that the model can be run in two modes: a basic mode, where you simply modify a configuration file and launch EVPV via a small command line interface, and a more advanced mode where you can use EVPV as a Python module to create some custom scripts. But in this video, I'll only cover the basic mode, which is ideal for users who are not familiar with Python or want to quickly run a case study. So to run the model in this mode, in addition to the input data, you will need a configuration file. And in this tutorial, to illustrate the full workflow with that configuration file, we'll use the Addis Abeba example, which is available in the example folder on GitHub. And you can later, of course, adapt this example to your own case study. So the first step is to download the folder containing the example. You can either do this by visiting the GitHub repository as shown before, or also by just clicking the link that you have here, which will download the entire example folder. So I've already done this and extracted the file, the folder here into a directory of my choice. When opening this folder, you will see several things. So first, at the root here, a configuration file which we will use, as well as also an example Python script for more advanced usage. And two folders, one containing the geospatial inputs here for Addis Abeba, and another one that for the moment is empty, that will be used to store the results. Now that everything is in place, we can already see how to run the study using the sample configuration file, which is already pre-filled. To do this, it's quite simple. So first you have to open an Anaconda prompt here in the folder containing the configuration file. Then activate your Conda environment, and then type just EVPV in the terminal and hit enter. So then you have to wait a bit, especially if it's the first time you run the model. The code then asks for the path to the configuration file. Since my terminal here is already in the folder where the file is located, I can just type directly the name of the configuration file here and hit enter. So this code starts running and display what it is currently doing. After about 1 minute, the execution is complete. And we can see now that the output folders contain 3 subfolders, each storing different types of results, which I'll explain in a moment, as well as a log file. In case something goes wrong, you will still be able here to see at which stage of the code. Let's take a closer look at the parameters and outputs. If I open the configuration file with the text editor, I see that there are 2 categories of parameters, some basic parameters and some more advanced parameters. We'll go through all of them, starting with the basic ones. So first here there are some general parameters. So here first the path to the folder where outputs will be saved, and a name for your case study. So if you change the name, it will affect the names of the output files, making it easier to save and compare multiple results. Next, there are parameters related to the fleet of electric vehicles. This includes the number of vehicles to simulate, here 1,000, and the different types of vehicles. In this example, I have two types named BEV and PHEV. The names themselves do not matter, but for each type I must define the battery capacity, the consumption of the EV, its maximum charging power, and also the share it represents in the fleets. So here we have 80% of BEVs and 20% of plug-in hybrid electric vehicles, so PHEVs. Then I have parameters related to the region of interest. So first the different path to the input files, and then importantly here also the size of the traffic zones, which defines the spatial resolution of our simulation. Note that this is here a target size in kilometers. The actual size may vary slightly depending on your specific region of interest. Then there are two parameters here linked to the simulation of distances between traffic zones. By default, if we set known here, the code will simply apply here this road to Euclidean ratio to convert straight line distances between traffic zones into estimated road distances. And in this example, I've extracted the average ratio for Addis Abeba. However, for more accurate results, it is recommended to replace here known with an OpenRoute service API key. An OpenRoute service is a free tool that allows you to calculate real road distances. And to use it, what you need to do is to create an account. You can directly go on the official website to do so, and then copy and paste it here to replace known. So these parameters determine the results found in the mobility folder. And if we open it, we see several files. So first here two HTML files. One containing the map of the region of interest with the geospatial data that is aggregated here by zone. And another one that I will not show you, but it looks very similar, is the number of vehicles that have been allocated per zone. And most importantly, here we have two CSV files, one containing the different vehicle flows. So it's this one, and the distances by road between, and also the straight line distance between the different traffic zones, which have here also an idea. And then we also have this other file which contains some more aggregated information by zone. So each row here is a zone, such as the number of outflows, the number of inflows, that are the vehicles that are coming in and out from work, the average distance per vehicle for that zone, and also the total number of kilometers that are traveled by all the vehicles of that zone. If we now look at the charging demand parameters, we see that they define some settings for each charging location, so home, work, and points of interest. And for each location, we must specify the share and the list of available charging powers. So here you have the power and the share of that charging power. And also we need to give the arrival time at that location. So here is the average arrival time and the standard deviation, except for points of interest where arrival times are calculated automatically. And so these parameters will determine the charging scenario, and the results can be found in the charging demand folder. Here again, we find first a few maps along with CSV files for the raw results. both about the spatial demand and about the temporal demand. So for the spatial part, we get for each zone here and each type of location, the number of vehicles that are charging, the total energy demand, and the average energy per vehicle. So for the temporal demand, there is first a file with the charging profile here for every single vehicle. So here every column is a vehicle. Then another file with some vehicle properties, such as name or the charging location for that vehicle, and so on. And importantly, an aggregated charging curve here by location type, which includes not only the power demand, but also the number of vehicles that are present at that location, and for a different time also the number of vehicles that are charging. So here it's very easy from that to get some kind of load curve, for instance. So here you have it for charging at home. And to finish, there are inputs related to the PV system. So these include the year of the simulation, the type of installation to simulate, the installed PV capacity, and the range of days over which to compute EV complementarity indicators. And here the results are stored in the corresponding folder again, including the annual PV production and some complementarity indicators over the selected days, like the self-sufficiency ratio, self-consumption, or excess PV production. And finally, we can look at the more advanced parameters here. So we have parameters related to the traffic zones. So here we can set if we want traffic zones or not to be clipped to the region of interest. Then regarding mobility modeling, there are some parameters that define here what model to be used for a trip distribution. Also what influences the travel behavior, which is influenced by the zone attractiveness. So for instance here what makes a zone attractive for work will be the number of workplaces, but you can also set it to population. And on the other side you can define some kind of travel cost feature, which for the moment here is the distance per road, but you can also set it to the straight line distance if you want. And there are also some, you can add some optional randomness and also an additional distance for other purposes than commuting. Then regarding the charging simulations, charging sessions are modeled with a specified time resolution that you can change here, and you can also change the charging efficiency. For PV simulation, you can change the PV module efficiency, the temperature sensitivity, and also the overall PV system losses. And finally, for calculating the EVPV complementarity, you can also add here a probability of recomputing the daily charging needs when you are calculating the daily indicators in order to account for some day-to-day variations in the charging load curve. And so this is especially important if you have a small number of vehicles, so potentially a high relative day-to-day variability.